So CUDA, NVIDIA's language and developer platform, was a huge gamble. GPUs were for graphics, but nobody was using them for computing. But NVIDIA believed something that others didn't.
And this was completely counterintuitive to repurpose graphics cards for general purpose computing at the time. It started in supercomputing with academics and scientists, but it set the stage for everything from AI to modern chip design today.
Yep, and joining us to break it all down are Dr. Satoshi Matsuoka, who led the Sububame, which was the first CUDA-powered supercomputer, Dr. Anirudh Devgan, the CEO of Cadence and a leader in chip design innovation,
and of course, Pat Gelsinger, the longtime chip industry executive, Intel executive, and recent CEO of Intel. Thank you so much to all three of you for joining us.
Thank you. Great to
Very
have
good.
you here.
Great to be here.
Great.
Well, Pat, we thought that, sorry, Dr. Matsuoka,
Okay.
you built the first GPU-based supercomputer. Tell us that story. How did you get the idea? Did you think this would work? Did you envision we would be here someday?
On this stage, no. Of course. The idea first came because I was working on supercomputers for a long time, and then when of course, reading up on these magazines and tech journals, then this thing called the programmable graphics pipeline started appearing as proposals from several GPU vendors. I said, then look at the schematics and everything. It's like, this looks familiar.
And it's essentially like repurposing programmable shaders and
Yeah.
trying to use that
Yeah.
to do broader computing
Yeah.
tasks, right?
Well, but the reason we came to the conclusion this was reusable, it looked very familiar to the traditional vector supercomputer architecture. But it's going to be a single chip. Okay, maybe we can use it for computing non-graphic stuff. Of course, there were lots of shortcomings in the early days. But then we tried various things. It didn't quite work out because there are some limitations. Then the CUDA GPUs started coming out. Had the right architecture. Instead of trying to fudge the programming into the graphics pipeline, it had this new language, CUDA, which was essentially a sort of like a SIMD type, a single instruction multiple data language, and meant for parallelism. We look at the language that maybe we can program this. A lot of our traditional supercomputer algorithms, we tried that and worked superbly. So
And
that
were
was
you buying GeForce consumer-grade graphics cards at this point in time?
Yeah, so the first supercomputer we had built was, of course, we had some small equipment in a test lab, but the first, moderate-sized machine was, by today's standards, it's tiny. It was a 128 GPU machine back in 2007, and this was sponsored by Microsoft. And the aha moment when we thought, this is going to be really usable in production is there was this supercomputer Blue Gene made by IBM and was running this this what's called protein docking code. You try to dock two proteins together, running a Blue Gene. Our team, my software team, along with the biology team, ported that over to this GPU cluster, which must have been like 1/20th to 1/50th the cost. It ran 4 times faster than Blue Gene.
Wow.
So this was the moment when we thought, this is going to be used in production, and then came Sububame afterwards.
Pat, I have a question for you. So you're at Intel at this time, and at least to me, at this moment, NVIDIA is sort of this peripheral thing. Like, they're a graphics card maker, and there's some academics that are doing cool things with it.
You let them live on your motherboard.
Barely.
What did you make of all of this, and did you think it was intriguing enough that it could become this type of market today?
Yeah. And, it was a fabulous time for the CPU, right? It was the king of the hill. And remember, what's a processor, right? You're running workloads. And the workloads of the day were operating systems, databases, virtualization, getting underway. and that was where the energy was in the developer and application community. And if you wanted to build a supercomputer, you just stuck a lot of them together over some mesh, an operation. And Jensen and I had numerous conversations about throughput computing. Today we refer to it as accelerated computing versus scalar computing. Branch prediction and short latency, pipelines versus, hey, who cares how long the pipeline is, just maximize throughput and create the programmability. And obviously at the time, hey, the CPU was the king of the hill. But, and I applaud Jensen for his tenacity of just saying, no, I'm not trying to build one of those. I'm trying to deliver against the workload, starting in graphics, but became this broader view. And then he got lucky, right, with AI. And one time I was debating him, he said, no, I got really lucky, right, with the AI workload, because it just demanded that type of architecture. And obviously, today, that's where the center of application development is, right, around AI, around these machine learning algorithms and so on, but we're not done, right, in that sense. And there's a lot more to be done, and I'm not sure all of those are going to land on GPUs into the future.
Because it's really the question of, is this workload parallelizable, right?
Yeah. And I mean, the AI workload is insanely parallelizable.
Embarrassingly parallelizable, I think is
right.
the term.
Because you're parallelizable across arrays, right? We were building 64 and 80-bit precision floating point. Now we're talking about 4-bit precision, and could we go to unary, right? This is just nuts in comparison, right? But again, I really applaud the team at NVIDIA because, under Jensen's leadership, they really saw that vision. But today, if we think about, for instance, the training workload, okay, that got to give way to something much more optimized for inferencing. A GPU is way too expensive. I argue it's 10,000x too expensive to fully realize what we want to do with deployment of inferencing of AI. And then, of course, what's beyond that? Right, and when I disagree with Jensen, I think quantum computing, we'll have it before the end of this decade in realizable form.
You think in the next 5 years we're going to have quantum computing in production?
Realizable quantum computing, yeah, absolutely.
Wow.
Right, and so the data center of the future, right? You're going to have some, traditional CPUs running portions of that workload, data handling, et cetera. You're going to have, training workloads. You're going to have inferencing optimized workloads, and you're going to have QPUs, quantum processing units. And if you think about quantum, most of humanity, right, most of the interesting things in humanity are quantum effects. So having a model of computing to look at those things is very appropriate, just like the GPU looked more like the brain for training and human and language and all of those things. So, I truly believe that that's the data center of the future, all three of those.
So right now we're kind of talking about this late 2000s, early 2010s era of NVIDIA's accelerated computing before we get to the Transformer paper, the explosion of AI. Could you, if you were rewinding all the way back then and you're having dinner with Jensen and you're trying to pitch him, here's all the things that are going to be hard about going from what you do today to becoming a generalizable computing platform, what does that list look like?
Well, it was very much around the programming model. Right, and we debated substantially because they had a 10x flop performance versus most of the CPUs, so we had projects trying to work to close the flop gap. But the reason that the GPU was an ugly machine was it was an ugly machine, right? It was not programmable. You didn't have good models for how to take advantage of that throughput. And that gap lasted a long time until CUDA got more and more functional over time. And the workloads and the developers started to align to that model of computing. And, here we are. This is stunning, what's happened. Like I say, we got really lucky, right, with this workload, but we're far from done.
Yeah. Anirudh, I'm curious in your world, when did you first come across accelerated computing and start to think, oh, this could be important for the future?
Absolutely. So what we do is we make software to design chips and electronic systems.
A lot of customers here today.
Yeah, a lot of customers. We're glad to work with all the big companies in the world. And this software is like, basically what I say is computer science plus math. It's like numerical software, mathematical software. This is not your typical software. So over like 30 years, the industry has optimized this software intensely. And so we are always looking for the best hardware to run it on. But my training, we are like software by nature. So this is always the search for what is the best computing platform. So even from the 90s, and of course it used to be CPUs, but what the whole point of, I think, NVIDIA's rise is the software drives the hardware, okay? And we're always looking for a massively parallel system, because, after a while, like even by the late 90s, it was clear that the CPUs are now going to scale, the power limit. So I did a lot of parallel computing in the mid, like 2005, 2006 timeframe, and we had to do it through CPUs, okay? But there's this trade-off of how complicated a CPU is and how many do you have, right? How complicating is the compute? And CPUs those days were very complicated because they were trying to do superscalar, all these things. Whereas GPU is less complicated, but there is a lot of them. And there's this trade-off, how many computing elements versus how many not. But this is all driven by the software workload. And some software workloads are very parallelizable, like matrix multiply, which is AI, and some are less parallelizable. So I started experimenting with GPUs from 2005 onwards, and they were good, but I think they got really better. So I have to credit NVIDIA by really improving the generality of GPUs.
And to Pat's point, the programming model,
right.
Making it actually usable.
Also from from 2005 onwards or 2010, what we are always looking for, software people, is we want the CPU and GPU to be close to each other. See, what happens is in the beginning...
That's going to be a huge issue going forward as well, right? How you be able to share memory across those environments, what the fabric architecture looks like, what's the memory, semantics that you're going to have, right? Is it shared, is it cached, is it coherent?
And CPU has a lot of benefits, like it's a conditional thing. If something is conditional, CPUs can handle it. And AI also, when it starts off in the last few years, is very brute force. It's like a dense multiply, but that will get optimized. See, even when chip design software started, it was dense matrices. Then it went to sparse matrices. Then it went to all kinds of latency partitioning, which is what is happening in AI now. So the AI workload also will become much more complex. So it will also need the CPU. So the good thing, I think, not only is the GPU, but I think what NVIDIA has done really well recently is this combination of Grace Blackwell or Grace Hopper, because you always want CPU close to you and enough CPUs.
Right.
And then a lot of compute elements with GPU. So this kind of CPU, GPU together is finally now a very good platform for people like us to optimize our software.
So I'm curious about that in particular, your software. You said that the workload kind of drives the architecture that makes sense, the software workload. For the software workload of chip design software, how parallelizable is the task? And how are you looking at migrating the way Cadence software runs from CPUs to GPUs, or is it just not make sense to run on GPUs?
No, we already run on a lot of software on GPUs.
Yeah.
Okay? And the work, we do have all kinds of workload. It's not one software. Some workload is very difficult to parallelize. Some workload is very easy to parallelize. See, like for example, matrix multiply is very easy to parallelize, like AI. So there is like system simulation, right? When you do like fluid dynamics or thermal simulation or weather forecasting, that's very similar to AI workload. But when you do like matrix inverse, it's very difficult to parallelize. Instead of multiply, matrix inverse. So we have like other kind of simulation, like transistor simulation. It's matrix inverse is very difficult to parallelize. But we have done those algorithms. These are proprietary algorithms from like 10 years ago to even parallelize not easy to parallelize thing. That's where the software. And I think GPUs are getting better and better to do that. But then there are other algorithms which are purely, integer-based performance, like Boolean operations, So that's but I think that's why I'm saying, one thing is the GPUs and, like especially Hopper and all have come a long way and Blackwell. And then with Grace together, it gives a very rich platform. So we are able to, we're going to announce a lot of stuff, today and next few months on accelerating on Grace Blackwell.
Yeah.
And we can do the entire suite now with that,
Well, people are talking about, ultra-dense compute capability. But when you look at, we run big supercomputers. Our supercomputer has 160,000 nodes. And it's called Fugaku, And next generation will probably go with GPUs, whether it be NVIDIA or not, we don't know yet. But one thing, when we do this comprehensive analysis of the workload, as you say, when you look across these supercomputing workloads, majority of them are bandwidth bound. I'd like to stress that one of the observations that was made very early, like when building very early GPU supercomputers, I said, look very much like a traditional vector supercomputer. Well, vector supercomputers were all about bandwidth, memory bandwidth, network bandwidth.
So it's not just the compute. It's about
not just the
making
compute. So that's why GPUs have HBM.
I've joked that the GPU is the most expensive memory controller that's ever shipped.
Right. So,
Spoken like a real CPU guy.
yeah.
But it is. If anytime it's sitting there waiting for memory, right? It's basically a heat-producing memory controller waiting for it. So that balance of memory, right, bandwidth of the memory hierarchy, and how it fits to the compute elements of the GPU is super important.
Yeah. In fact, 70 to 80% of the workload are bound by memory, and not by compute.
Yeah.
So the GPUs having this vector computer-like architecture to drive the bandwidth.
Yep.
As well as facilitating modern memory like HBM,
Yep.
really helps to accelerate the workload. And this is even true for AI, because transformers are not just about matrix multiply. Half of the time, the transformers spent accessing memory because there's a fully connected layer. There's a layer that does the matrix multiply, multi-head attention. But then there's a fully connected layer, which is all bandwidth bound. So about 50% is matrix, 50% is memory.
And that's why I think some of the future, particularly inferencing optimized chips, will be much more focused around things like in-memory computing, right? Where you bring the memory and the computing elements. You have low radix math that you're doing, and that's why I think inference optimization, right? Will get a different chip architecture that will be optimized around the memory subsystem.
Is anyone shipping in-memory compute right now?
Oh, several. Some of the companies are starting to as well. None of them to me have quite matched yet the programmability across a range of workloads, but I think they're getting close. There's about half a dozen companies. I happen to invest in one of them, Fractal, right, that's working in this area, but there's a couple others like D-Matrix that are focusing. And, we need to make inferencing 10,000 times more efficient. That's going to take some pretty novel breakthroughs, and a lot of it's going to be exactly in this area of what the memory hierarchy looks like and how memory and computing come together.
So one thing I do want to mention about Jensen and NVIDIA, because people always say, like this, I watched, Jensen and NVIDIA for the last 20 years, definitely last 10 years. And everybody says...
Some of us argued, some of us fought with them, some of us loved them.
We'll come back to that.
And we worked with them closely for 20 years now. So I think a lot of people say, GPUs are good at X, but for Y, you need something else, okay? But that X is not constant. The good thing about NVIDIA, they always innovate. They have a yearly cadence now, innovating, adding not just compute, but the architecture. So I think NVIDIA, what is remarkable, and their connection to the software ecosystem.
Yeah.
And they work closely with us, they work closely with other kind of software companies to know what is coming. So I think sometimes people make a mistake of looking at NVIDIA or GPUs in a very static way. It's not a static thing. It's a dynamic thing, and it's changing very fast.
Certainly
and they adapt very well to it.
This is an incredible achievement in this era. This was a developer relationships in the first era of NVIDIA meant video game developers.
Yes.
And then they came to you, and then they came to industry, and then they came to all
So I think Jensen Superpower is connecting not just with the users of his products, but with the developer community and knowing what they need and moving NVIDIA forward. And this is really a great thing to see over the years. So I think to assume NVIDIA is static is a big mistake. They're the most dynamic.
He's back there planning 1-2 GTCs from now.
Exactly.
He's like barely focused on today.
So that's the real strength of their operation. Yeah.
Pat, you mentioned earlier this kind of crazy phenomenon that is the graphics cards that they made were an architecture that were really, really good for graphics rendering. And then they got very lucky that at some point in the future, the transformer paper would get invented, and then they would be this unbelievably well-suited thing for the AI era. Is there another version of history where that could have been Intel or that could have been someone else? Did it have to be NVIDIA? being at the center of this universe?
Well, clearly, I mean, I had a project that was well known in the industry called Larrabee.
Larrabee, yeah, exactly.
As well, which was trying to bridge the programmability of the CPU with a throughput-oriented architecture. And I think had Intel stayed on that path, the future could have been different at that point. And as I said, I give Jensen a lot of credit. He just stayed true to that throughput computing or accelerated, computing vision that, brought them to this point that the workloads said, where can I get the best result? Workloads aren't these magic things in that regard. People, software algorithms are trying to solve hard problems. And what's the best hardware platform to do it on? And it takes them a couple of years to port and optimize, for it. And hey, he was true to that vision and what we have today. But there's workloads of tomorrow, and people are innovating what those look like. And as I said, I think inferencing needs a better architecture. I think that quantum will emerge as well, because hey, those algorithms don't fit on classical computers of today, and most of humanity runs on quantum effects. Right, and most of the interesting problems are quantum related, and having a quantum architecture for quantum problems, I think will open up entirely new dimensions of computing future.
When you say most of humanity runs on quantum effects, you mean like the
well,
life was
semiconductor is a quantum effect, right? When you think about it. So you go to a quantum, most of biology benefits from quantum effect. So I'd say most of the unsolved problems, leverage quantum effects, right? And also, we're going to be operating much more at cryogenic temperatures going forward, right? So you're going to see many of those things like superconducting will come into it. You'll also be able to, open up, we're scratching the surface on composite materials, right? 2, 3, 4%, of the magnetic materials have been explored. Right, we have enormous portions of that for better magnetics. Many of the medical breakthroughs are limited by computing. And again, most of those algorithms were going to fit much better on a quantum machine, than they do on today's classical machines. That's why I say this is a thrilling time to be a technologist. Just thrilling. I just wish I was 20 years younger to be doing more. It is that good. Well, but maybe medicine will give me another 20 years.
Eat well, sleep.
Yeah.
Dr. Matsuoka, are you seeing, do you use quantum in your lab?
Well, yes, as we speak, we're bridging our supercomputer, one of the leadership supercomputers, Fugaku, with multiple quantum machines that we are partnering with a company like IBM, Quantinuum, etc. And also, RIKEN has its own quantum center, developing our own quantum computer. But the future, we believe, will be hybrid. So there are certain things when quantum computers really excel at, when there are some problems when quantum computers are not really advantageous.
Quantum, right? Will be next to accelerated, next to classical.
So it really it really helps to have the best of both worlds. That is to have two collaborate, and then do stuff that what's good at, and combining the two really excels. We found really excels the ability of the future computers to solve difficult problems that Pat mentioned. So in fact, we have such several results in that already. Some of the problems that even the biggest supercomputers could not solve, we're starting to solve in this hybrid environment. So we're investing quite a bit in this quantum classical hybrid computing, and certainly for certain problems, that's going to be the answer. But that said, for a lot of other things, GPUs will also be great too.
Also quantum, of course we work with a lot of quantum companies because they design the chips, Cadence, we work with almost all of them. But I think we should be careful that, there is a lot of benefit to scale. Computing has to be done at scale. When we run our software, or when, with the AI workloads or traditional workload. So silicon has a lot of scale. So I think of course, quantum has a lot of potential for certain applications. But I would not count out silicon anytime soon.
No.
Because,
silicon too.
But let me pile on that.
Please.
The quantum effects or the quantum solutions I'm intrigued by are all building on silicon. There have been trillions of dollars invested into silicon, right? Manufacturing, scale, understanding. silicon is like God's gift to humanity. You can bend it, you can shape it, you can manufacture it. It's a new, 4-4, you can put things into it. So I believe the realizable million qubit machines that I believe will emerge this decade, will be based on silicon manufacturing for quantum effects and qubits.
Oh,
Wow, future's exciting.
Yes, indeed.
Well, I think that takes us to the end. Thank you so much
we're not
for
done.
joining us. Really appreciate it. Each of you
break.
obviously have, very different backgrounds. Academia, Cadence. I think basically software that is used by every single chip designer in the world in some way,
Including NVIDIA itself.
including NVIDIA,
great
including the biggest companies in the world. And Pat, I just think you've seen a very interesting perch, and the world could have evolved in a lot of different ways. And I think it's really interesting. I keep going back to your comment, lucky. Lucky that it evolved in this way with NVIDIA and Jensen sort of bending the universe a little bit toward NVIDIA's GPUs.
I love, the great Bell, comment. The harder I worked, the luckier I got. And I really believe, NVIDIA created a lot of their luck, right, in that regard. And, it was decades of hard, contiguous work in a singular direction that allowed them to bend the universe in their direction right now.
Well, guys, thank you so much.
Thank you.
Yeah, thank
A
you.
big thank you to our guests for taking us through that chapter.